Okay, so now what we're going to talk about is the following. So again, the point was, so here's Newton's second law. Force is dp by dt, rate of change of linear momentum. And the neat thing about this law is valid for a single particle, and it's also valid for a system of particles. So when you're considering a system of particles, this will be the total momenta of the system of particles, and this will be the net force on the system, meaning if there are individual forces acting on individual particles, you add up all the forces. So this would be the net force, and this would be the momenta of the system of particles. Again, this Newton's second law applies for a single particle and a system of particles. Okay, so that's what we're looking at here. Okay, so here's a system of particles. So 3 particles in this case, and there's F1 acting on this guy, F2 acting, 3 forces acting on them. You can add the 3 forces, 1, 2, 3, and there's the net force. And what this equation is telling you is, so Newton's second law is telling you is the net force acting on the system is equal to the total mass of the system times the acceleration of the center of mass. There's the center of mass of these guys, and the center of mass accelerates. The acceleration of the center of mass is given by this equation. Okay, so this equation, which applied to a single particle, also applies to a system of particles. Okay. Now, when you do the collision slab, you will see the center of mass, and since in a collision there's no external force, this is 0. The center of mass acceleration is 0, and you'll see that the center of mass moves at constant velocity. In the simulation, you'll see objects colliding, and so note that, and that's fairly neat. Okay. Okay, so we saw this slide earlier, so I'll skip this. Okay, now we'll talk about rocket propulsion. Yeah. So here's another topic of interest to us, and essentially what rocket propulsion relies on is the following. So here's a good image to have. So let's say here's a cannon. Here's a system. Okay, so here's a cannon inside a vehicle, and before the cannon is fired, let's say this was at rest, so the momentum was 0. Now when a cannon is fired, the cannonball has a momentum in that direction, so this object must recoil. It will recoil such that the total momenta is 0. Okay, and you keep firing cannonballs, and your recoil velocity will keep increasing such that the total momentum of the system will be 0. And that is what is happening in a rocket. The rocket keeps firing hot gases in this direction, and so a rocket keeps recoiling in the opposite direction, so that the total momenta of the system is always 0, assuming this happened in free space and all that kind of stuff. Okay, so the operation of a rocket depends on the law of conservation of momentum. If you fire something in that direction, you recoil in the opposite direction. Okay. So here's a situation we'll consider. So imagine this is happening in outer space, far away from any gravitational field. So here's a rocket going at this velocity, and right now its mass is that. And the way this rocket speeds up is it spews out some hot gases, it fires hot gases in that direction. And so because it's recoiling, its velocity increases. Okay, so now this is an explosion, sort of, this gas went in that direction, and so the rocket recoiled at a faster rate in this direction. Now, the momenta of this rocket before the at this point was the initial momentum was its mass times its velocity. Yeah. Now the momentum of this hot gases that's going in that direction plus the momentum of this guy should equal this initial momentum, and that's what this equation is saying. So there's the initial momentum, there's the momentum of the rocket, which has sped up a little by that much amount, and this is the momentum of the hot gases. That's how many hot gases was exhausted. That was the initial velocity of the rocket, and that was the exhaust velocity. So this is the momentum of the exhaust gases. Anyway, you can go through these equations, and what you find is this is the final equation. This is the result you arrive at. And let me go over this equation. What this says is, so if this were in deep space, this rocket is, its engines are firing, and what this equation is giving you is the final velocity of the rocket minus its initial velocity is equal to the exhaust velocity of the gases. This is the exhaust velocity of the gases relative to the rocket. Natural log of initial mass times divided by final mass. So as the rocket is burning fuel, its mass is decreasing. Okay. So what this equation really tells you is, if you want to achieve a certain final speed, so for instance, the space shuttle had to go at 8 kilometers a second to be able to orbit the Earth. Okay, so this equation will tell you how much fuel you need. This is the mass of the rocket with the fuel, initial mass of the rocket and fuel, and this is the final mass of the rocket after it's burned all the fuel, and that's the velocity to achieve. Anyway, so that's what this equation is useful for. Okay, now we'll we'll give you a better approximation. This is if it were in outer space. We'll show you how to take into account Earth's gravity. Okay, what this tells you is, it gives you the rocket thrust. Mass times dv by dt, that's acceleration, so that's the thrust or the force that the engine exerts on the rocket. And it can be shown that's equal to the exhaust velocity of the VE stands for the exhaust velocity, and dm by dt, that's the rate at which the mass of the rocket is decreasing, and so that's why we have the absolute sign, so that can be positive. That's the rate at which fuel is burning. Okay, the rate at which the mass is decreasing gives you the rate at which fuel burns. Okay, so the thrust, if you want a large thrust, what you want is either have a large exhaust velocity, but the exhaust velocity depends on your fuel choice. So once you've chosen the fuel, that's fixed. So if you want a greater thrust, you just have to burn fuel faster. So that's what this equation is telling you. Now let's look at the rocket in a gravitational field. So when the space shuttle was sitting on the launch pad, it had to deal with the Earth's gravity. So the previous equation, now the final velocity of the rocket is minus initial velocity of the rocket, gets changed by this term. Is the exhaust velocity natural log of initial mass divided by final mass minus g times the burn time. This is how long the rocket was and the engines were fired. So g times that. So for instance, for the space shuttle, it took 8 minutes to get to orbit. Okay, so anyway, so with gravity present, that's how this term gets added. Okay. So anyway, with this equation, you can calculate the final velocity. To achieve that final velocity, you can calculate how much fuel you need. Okay. All right, so we'll quickly go over some numbers for the space shuttle. So it took the space shuttle 8 minutes to get to space, and its orbital speed was 27,000 kilometers per hour, roughly 18,000 miles per hour. The average acceleration was 16 meters per second square. That is 1.5 Gs. So that was the average acceleration. Yeah. The space shuttle was pretty amazing. So These were the three main engines. These are the main engines. And when it was sitting on the launch pad, this thing was so heavy that you needed boosters. Okay? So these were the boosters. These guys burned for 2 minutes. These guys burned for eight minutes. So for the first 2 minutes when the rocket was heavy, you needed these boosters. And after it got to a certain speed and the weight had decreased, these boosters were ejected. Okay. This orange thing is a fuel tank. It was liquid hydrogen that was being burned. So it had a liquid oxygen and liquid hydrogen. We'll come to that in a second. So these are the three main engines, and these are the solid rocket boosters. The three main engines and two solid. So these 5 engines together generated a thrust of 7 million pounds. Okay, by the way, this is 10 to the power 6. The iPad is not rendering it properly. So it read these 5 engines generated 7 million pounds. So you could essentially lift a 7 million pound object. The rocket, how much did the shuttle and everything weigh? This is in kgs, 3.3 million kgs of thrust. And it weighed 2 million, so 4.5 million pounds is what it weighed. And again, these are in kgs, so the thrust was roughly 1.5, 1.6 times the weight of the object. Okay. Of course, if the thrust is less than the weight, you're not getting off the launch pad. Okay. So your initial thrust has to be greater than your weight. Okay, so here's again some numbers. So the main engine exhaust velocity was 10,000 kilometers per hour. So the hot gases coming out of the main engines were coming at 10,000 kilometers per hour. Yeah. So that's 3 times that of a high-powered rifle bullet. And at these exhausts, the main engine were burning fuel at 12,000 kg per second. So the main engines were burning fuel at 12,000 kgs per second. With a small car weighs 1,000 kg, so that's 12 small cars a second. That's how much fuel was being burned, and the fuel was stored in this orange tank. The solid rocket boosters, they burned 4,500 kilograms of propellant per second. So they were burning 5 cars per second. And again, like I said, these guys worked for 2 minutes, 120 seconds. With this, so the maximum power output of the 3 space shuttles' main engines, you saw the main engines which burned liquid hydrogen had a power equivalent of 20 Hoover dams. So a Hoover dam running at full power can run 1 million homes. So those shuttle engines could run 20 million homes. So it was 40 million horsepower. And that's just the main engines. Okay, so these 3 main engines that burned for 8 minutes had a horsepower of 40 million horsepower. Okay. So the shuttle was a pretty amazing machine. All right, that finishes the lecture. Okay. So I'm going to stop the recording.